Awesome. Thank you. I'm so happy to be here and invited to give a talk on deep dive into the Stark Platinum Prover, which is our implementation of the Starknet Stark Prover. So we wanted to give you an idea of how this prover works, what are its basic principles. And so, well, we just gave a workshop a few hours ago where we gave like some basics and dived into the code. So sorry if I repeat some of the concepts, but I want to make sure you understand how this works. So this is the outline of my presentation. First, we're going to speak about what Stark Platinum is. Then we are going to talk about Starks, and there we will see like the main steps: arithmetization, interpolation, composing constraints, the Fry protocol. Then we will talk a little bit about the security, and then what is the roadmap, because right now we are working towards full compatibility with the Stone Prover, which is Starknet's current prover, and we want to make some optimizations also, so we can talk a little bit about the roadmap. Okay. So what is Stark Platinum? It is, as I told you, our implementation of a general Stark prover. It was written in Rust because we wanted to have a secure and performant implementation. It can be used to prove Cairo code. You can call the Cairo VM to execute your Cairo code, generate an execution trace, and then prove it. And right now we are working towards full compatibility with the Stone Prover. I think that in a few weeks we will be compatible with the plain layout, and in some weeks later we will have like the full compatibility with the recursive layout of Starknet. So there are like different layouts for the prover, and we have to implement each of them, and we are in the middle of everything and documenting all that so that anyone who wants to have their version of the prover can implement it and also understand how it works. Because we think that there is like no decentralized setup if you don't understand fully how everything works. We just say verify, don't trust. Okay, so Starks, how do they work? First, Starks is just an acronym for Scalable, Transparent Arguments of Knowledge. This means that Starks don't need a trusted setup, and they are conjectured to be post-quantum secure because the security depends only on the hash function. It's widely used in many validity rollups, and it has like 3 main ingredients, which are Merkle trees, for which you need a hash function. Then we use polynomials to encode the information, for example, from the trace, and read Solomon codes. So the first step is what we call the arithmetization. So the thing is, to prove the program, we need to transform our code into a set of polynomials. And we have like 2 main elements. One is the execution trace, which contains all the values of the registers as they evolve during the program. And then there are like some constraints that have to be enforced over that trace for it to be valid. For example, if we have a variable that is Boolean, then we need a consistency constraint that ensures that our variable is either 0 or 1. Then we have like some boundary constraints, which are those we need, for example, to show that the registers have been properly initialized and have the values they are supposed to have. And of course, then we have transition constraints, which tells us that we made a valid transition from step I to step I+1. And well, these constraints are dictated by the error, and of course that depends on, for example, the VM you're using. In the case of Cairo, you have the Cairo error, which is supported in our library, But of course, if you use, for example, a VM like Maiden, you have its own algebraic intermediate representation. So that depends a lot on the program you want to run. But once you have it, then of course you can prove any program. So as I told you, the execution trace is just a table containing the values of each register at every step. So imagine just that as a very large table. And so what we have to do first is encode the trace as a set of polynomials. So what we are going to do is choose some interpolation domain and interpret each value as the evaluation of a polynomial over each point of the domain. So what we have to do is an interpolation so that we encode those columns as polynomials. And to make sure that the prover doesn't cheat, we have to commit to the execution trace. And the way we do it is by using Reed-Solomon codes. So what we do is we choose a larger domain and we evaluate the polynomial. Of course, since the polynomial has degree n, evaluating over m larger than n, there are only n of those values that determine the polynomial. So if we cheat or something, people will know that we are doing something wrong because the polynomial will have a higher degree. And so what we do is, to commit, we build a Merkle tree, which is just a binary tree built from the evaluations and using the hash functions. So what we do is we get to the root and we give the root to the verifier so that he knows that we committed to any of these values. If we try to change and pass one value which is not included in the tree, then because the hash function is collision resistant, we shouldn't be able to find a valid authentication path to get to the root if we are passing like wrong values. And well, then we have the error constraints. So as I told you, for example, we have conditions for consistency. The first one we have is a Booleanity constraint, because if that polynomial C1 of x is to be 0, it can either be 1 or 0. Then, for example, we could have a transition constraint where we say that the next value is the square of the current value. And what we do to enforce the constraints is we plug in our trace polynomials into these constraints. And if they are valid, these polynomials should evaluate to 0 over the interpolation domain. How do we prove then that these polynomials are 0 over the domain? Of course, we cannot pass all the values because that wouldn't make our argument scalable. That is to say, the proof wouldn't be short. So what we do is, instead, we show the divisibility of those polynomials by a vanishing polynomial over the set. So what should happen is that if we take these new composed polynomials and divide them by the vanishing polynomial, the result should be a polynomial. If it is not, then this is a rational function. And then, of course, the proof would fail, because what we need is to prove that this is in fact a polynomial. Well, there is like some little trick because we have many constraints, and that's why we take a random linear combination and reduce this to a single check of what we call a composition polynomial. And how can we prove that this linear combination is a polynomial? Well, here comes like the main ingredient of the protocol, which is Fry. So Fry is a proximity test based on Reed-Solomon codes. And the thing is, it allows us to test whether a function is close to a low-degree polynomial. So this means we are likely to accept this even if the function is really not a polynomial, but it is close to some low-degree polynomial. Of course, here we have a small soundness error, and of course, the Fry protocol can be used directly in the Stark protocol or as a polynomial commitment scheme. So many protocols are right now using it just as a polynomial commitment scheme, as is the case of Plonky 2. So to build Fry, we need an evaluation domain with certain properties. Typically, we will deal with the roots of unity because we will have like efficient evaluation techniques and we can prove things really nice. We will use linear codes. That's why we have Reed-Solomon, and of course Merkle trees to commit to all the evaluations. So what's the protocol like? We start with a polynomial. Of course, one way to show that something is a polynomial is just I give you all the coefficients and you check that it is in fact a polynomial. The problem is if our polynomial is very large, then we have to pass a lot of information. So can we do better? Can we reduce the amount of information we have to pass to the verifier? Okay, so there is one way we can do, but we need to interact with the verifier and ask him for some randomness. So what we do first is we commit to this polynomial so that the verifier knows we are not going to change it. So to do that, we use, again, the Reed-Solomon encoding, and we build a Merkle tree out of those evaluations. And so now that we have committed to that polynomial, we can ask him for a folding coefficient. It's just a scalar. And what we do is realize that we can split our polynomial between even and odd parts, and so define the new polynomial P1 from the even and odd parts. Of course, there is a problem because we have an extra power of x. So what we do is we replace that x by beta 0, and so we define a new polynomial in x squared. The thing is that polynomial will have a lower degree. Exactly, the degree is half the original degree. And so if we want to show to someone that that is a polynomial, we have just to pass half the coefficients. Of course, a good thing is, since we are using roots of unity, taking x squared means that we have like n over 2 different values, and so the Merkle trees will become also smaller, and so we'll have to evaluate over less points. So what we can do now is we have the amount of coefficients we would have to pass, and so we can continue recursively just by, okay, committing to a polynomial and asking the verifier for a folding coefficient, and go that way until, for example, we get to a degree 0 polynomial, where we just have to pass only one value. And of course, there we have a very short proof. And well, it will take more or less log 2 of the degree of the polynomial, and then we will have to pass some values from the different intermediate polynomials so that the verifier can check that we did everything correct. So what's the proof like in the Fry protocol? Well, the verifier can query our original polynomial at several positions. This will be the query positions, and for every query, what we will have to provide is first a set of values from the low degree extension of the trace, so that the verifier can check consistency between our composition polynomial and the trace, so that we didn't lie with the constraints. In Stark terminology, you call that the mask. Of course, then we have to prove that all those evaluations are in the Merkle trees to which we committed our evaluations. And then what we will have to do is, from every polynomial at every Fry layer, provide the evaluations and the inclusion proofs, which are just the authentication paths. So in general, the proof will consist of all the elements in the queries plus all the Merkle roots. And there are like some optimizations and changes we can make. For example, to reduce proof size, what we can do is skip some layers. So commit every, for example, second layer. And so we have to pass like half the amount of roots from Merkle trees. Another optimization is, instead of reaching degree 0, we can stop before. And then we have also, we just passed like the coefficients of the last polynomial, and we save like several authentication paths from the intermediate Merkle trees. Of course, there is one that it has to do with out-of-domain point to ensure consistency between the trace and the composition polynomial. And then there are like some optimizations that are used, for example, in the stone prover in our prover, which is avoid sending repeated elements, for example, from the authentication paths, or elements that can be computed directly by the verifier. And another thing is, in general, we have to pass 2 elements from every layer of the polynomial. So instead of grouping them, we can group them together in the same branch of the Merkle tree. So that is really more efficient. And to make it more performant, we can work with smaller fields. And of course, this has also advantages in terms of the VM, as they were discussing before, that they had a huge overhead because the current Stark prover uses a 256-bit field. And really, we have, for example, efficient fields of 64 bits. So that reduces a lot the overhead we have. And just to give you an idea, the security of the Stark protocol depends on 4 parameters. The first one has to do with the field size. So the field size should be much larger than the low-degree extension domain, that is to say, our evaluation domain. So in general, it has to be around 150 bits long or more. So if we work with a smaller field, maybe we can work with extension fields to achieve this condition. Then, of course, we have the hash function. As long as the hash function is secure and provides the adequate bits of security, that is not a problem. So right now, of course, working with SHA-3 and 256 bits of security is sufficient. If quantum computers were to appear, well, we just have to increase the size of the digest, which will increase proof size. Another thing is the number of queries. So each query adds to some bits of security. So by adding more queries, we can increase security. And then, of course, we can add proof of work to increase the cost of a prover cheating and trying to generate favorable queries. Well, there are like some major steps towards compatibility with the stone prover. So right now we finished with Merkle trees, proof generation, the proof serialization and deserialization, also the proof of work. And now what we have to finish is the algebraic intermediate representation for Cairo. We have to organize the constraints exactly in the same way as the stone prover. I hope we will get very soon to the plain layout, and so you will be able to verify directly in the L2 verifier simple programs in Cairo, and then we will have to add the built-ins, and so you will be able even to prove recursive programs. So thank you very much for your attention, and if you have any questions, I'd be more than happy to answer. Thanks.